Hello, gentlemen. Welcome back. We're going to start looking at rational functions now. And I'm going to break this section up into three different videos because there's a lot of material here. So um, make sure that you're really paying attention and taking some good notes because this stuff can get a little bit complicated. But let's get started. Uh, let's talk about rational functions. First, we have to define what a rational function is. A rational function is in the form where I have a polynomial in the numerator and a polynomial in the denominator. Okay, so I have a ratio of two polynomials. Very important thing that we have to look at first and foremost, going all the way back to domain. All right, we need to look at the domain, and the domain is going to be all real numbers that do not make the denominator zero. If I have zero in the denominator, you know I have a problem. Okay, so that's number one. We want to identify our domain. We need to determine the behavior of the function near these values where the denominator does become zero. Okay, and we're going to talk about vertical asymptotes, and we're actually going to introduce a concept called limits, which is some calculus terminology that you're going to need to know. And then we need to determine the end behavior of these functions. What happens as the function, as x approaches infinity and as x approaches negative infinity. Again, we're going to use this limit idea. So let's take a simple example here. Let's graph the function x squared minus 1 over x plus 1. Okay. Fx a rational function. We have polynomial on top and bottom. We need to determine the domain. Again, when we're looking at domain, we need to look at what happens in the denominator. We know that the denominator becomes 0 when x is equal to negative 1. So negative 1 is not in our domain. Okay, so that's automatically out. All other real numbers are going to be fine. Let's simplify this expression. You should note that I have a difference of squares up there. I can factor this out, and the x minus 1 terms are going to cancel. Now, even though this function simplifies down to x minus 1, we still need to understand that x equals negative 1 is not in the domain. Okay, because this is my original function. So when you're looking at domain, go back to the original function. So what does that mean? Basically means that f of x is going to act like a line, this line x minus 1, except it's not defined at that point. And there's just going to be a hole in the graph at x equals negative 1. So I'm going to have a hole here at negative 1. Otherwise, it's going to behave just like a straight line. Okay? So there's one type of situation where I don't have a value in my domain. This is a hole. This is actually called the removable discontinuity, which we'll learn more about later. Let's look at this function, though. This situation is a little bit different. The domain here, obviously, the denominator is 0 at x equals 2. So I got all real numbers except for 2 is in my denominator. Okay. However, this time I can't simplify anything further. I can't get rid of this x minus 2 in the bottom. And so now what I need to do is look at what is going to happen to this function as x approaches 2 from both the left and the right. In other words, I need to understand what's going to happen. I'm not defined at this point. I'm not defined at x equals 2. I want to see what the behavior is from both directions. Okay? Something a little different. I'm introducing this limit idea. This is a calculus term. This is something we're going to see towards the end of the course, but I want to introduce you to it. All it means is I want to find out what happens to this function as x approaches 2, and that little plus sign there means from the right. What happens as x gets really close to 2 from the right side? Okay? So as x gets close to 2 from the right, x minus 2 gets close to 0 and is positive. So when I say from the right, I'm coming in a little bit bigger than 2. So I'm actually going to approach my pen here. If I'm looking at 2 here, here's my line x equals 2. I'm going to look at values coming in from this direction. Okay? So x is always going to be a little bit bigger than 2. Let's say something like 2.000001. All right, that's coming in from the right because I'm a little bit bigger than 2. If I subtract 2 here, obviously I get a small number, 0.000001. Okay, that's what my denominator is going to be. And then if I divide 1 by that very small positive number, what do I get? Well, the result is a very large positive number. And so the closer I get to this value of 2, the bigger the function value is going to be, and so we say that that function is going to approach infinity. Okay? Hopefully that makes sense. Let's look at the other direction. What happens when I come in from the left? Okay, this is coming in from the left, and so x is close to 0 from the left. This time I'm coming in from this direction, so I can say something like 1.999999, etc., minus 2. Again, this number is going to be 0.000, a bunch of zeros in 1, let's say, but it's going to be negative because the 2 is going to be bigger than that. And so what we're going to get is 1 is going to be divided by a very small negative number, okay, very small, like negative 0.000001, let's say. And then I get a very large negative number, okay? So if you try this on your calculator, do something like this, go, 1 divided by negative 0.000001, and then just keep adding zeros here. What you're going to see is this number is going to get bigger and bigger and bigger. And so we're going to say that it approaches negative infinity, okay? And this leads us to the idea of a vertical asymptote. The line x equals a is a vertical asymptote if f of x approaches infinity or negative infinity from either the right or the left. And that's what we had in this situation. Okay? So x equals 2 is a vertical asymptote. Now what we need to do is look at the end behavior. What is the end behavior going to look like as x approaches infinity and negative infinity? Well, let's look at that. Again, we're going to use the idea of a limit. As x gets huge, as x goes off to positive infinity, what is the function going to do? Well, basically what it becomes, x approaches infinity, x minus 2 becomes a really large number, and it's positive. So I have 1, basically 1 divided by a really large number. Here's 1 divided by a really large number. 9, 9, 9, 9, 9, 9, keep going. That value right there, you guys should all notice, is going to be a very small positive number, and so the function is going to approach 0. Okay? Let's look at coming in from the other direction. Again, I'm going to approach negative infinity. The limit is to go to negative infinity. That becomes a very big negative number, so now we're looking at 1 divided by negative 9, 9, 9, 9, 9, etc. That's also going to approach 0, but it's going to approach from underneath. Okay, and so in other words, when I say from underneath, here's my thing. As x goes, I'm going to approach from this side here, and up here I'm going to approach down like that from the other side. Okay, and what we see here is that we now have a horizontal asymptote. The line y equals b is a horizontal asymptote if the function approaches a value b as x approaches infinity or negative infinity. So in this example, y is equal to 0 is a horizontal asymptote. Let's put all the pieces together. Okay? So if I want to look at this graph of x minus 2, 1 over x minus 2, are there any zeros? Well, you should see that there are no zeros because the numerator is never 0. The y-intercept, I said x equals 0, I get negative 1/2. Okay, remember that to find this, we set x equal to 0. Okay, here's my vertical asymptote. Okay, my vertical asymptote here is the line x equals 2. Remember, from this side I went off to positive infinity, from this side I went to negative infinity, and here's my horizontal asymptote right here. Okay? Again, this is going to take a little bit of practice for you guys, and I can have more than one vertical asymptote, as we'll see in some examples later. Here's some practice. This is just the first of 3 videos on this section, so be patient. You're going to get it. Okay? Look at these examples 1 and 2. All right. Here are some practice problems that talk about domain, and they talk about finding vertical asymptotes. Okay. Remember, vertical asymptote is where the denominator is equal to 0, and we can't cancel it out. We saw one example where we just had a hole, and we saw one example where we had a vertical asymptote. Okay, and then we also talked about horizontal asymptotes. Okay, gentlemen, this takes some practice. Make sure that you look at these problems. Email me with questions. I would do this set of problems first before I looked at the next video. Make sure you feel comfortable with these, and then go on to the next video after that. Maybe watch the next two and then do the rest of the problems. Okay? Have a good day, fellas.